classification or general loss.
Yeah, thank you very much. So I'm going to talk about, as you said, proper learnability and the role of unlabeled data. So this is joint work with some excellent collaborators at USC. You've probably noticed by now that Shaddin is here at the conference, and Vatsal is also here at the conference. So we're motivated by really a pretty fundamental question, which is, when are supervised learning problems properly learnable? And if they are, what kinds of proper learners actually succeed for them? Okay, and there's, I think, at least two reasons why you might be interested in this. One of them is that proper learners kind of tend to be simpler than other improper learners. Examples are empirical risk minimization, ERM. Another example is ERM with a regularizer for tie breaking. This is sometimes called structural risk minimization, or SRM. Another reason you could be interested in properness is that it's semantically a very meaningful condition. So properness, recall, is just, can I learn my hypothesis class using only hypotheses in that class? So for example, can I approximate the best decision tree only using decision trees? And relatedly, kind of, are optimization problems over H powerful or expressive enough to even learn the class H itself? So it has a very natural interpretation. To give you a little bit of background, you're probably familiar with some nice settings in which learnability by any kind of learner is equivalent to proper learnability going through uniform convergence. So this is the case in nice settings. Examples are binary classification, agnostic regression. But oftentimes this equivalence is kind of brittle to even small changes in the setup. So if I move to multi-class classification on arbitrary label sets, or if I go to realizable regression, then now all of a sudden I have a gap between proper learnability and improper learnability. So some problems can be learned, but only improperly. And so our perspective is really, under what assumptions on H, or on the information that I give to the learner, is a problem properly learnable? And I think kind of the best thing to really hope for is, can we get some kind of combinatorial characterization of proper learnability? So for example, for multi-class classification, can I get a properized DS dimension? That would be kind of the dream. And I'm going to be focusing on realizable supervised learning throughout. So for now, I want you to think of just a very general loss function, just kind of arbitrary loss function. Later on, I might need it to be bounded. I might need it to be a metric, but I'll make that clear whenever that comes up. So one angle that you can take to approach this is to ask, how helpful is unlabeled data? So kind of in the limit, I can ask, what if I give the learner an infinite amount of unlabeled data points? Or kind of even more extremely, what if I give the learner the marginal distribution on unlabeled data? Okay, and so we study this using what we call the distribution fixed pack learning model. Okay, before I flash the bullet points, this is just the pack model, except I give the learner the marginal distribution on unlabeled data. Okay, so to be a little more explicit, the kind of adversary picks a ground truth classifier, H star and H, and a marginal D on unlabeled data. This time, the learner gets the IID training set, but it also gets this marginal D. Okay, just kind of at a mathematical level, it receives this marginal. And as usual, everything else is as in the pack model. So I'm judging the learner based on worst case performance over all possible realizable distributions. Okay, all possible realizable distributions. We aren't the first ones to think about this. You might have seen this studied as the so-called utopian model of semi-supervised learning by Liu and Ben David and Liu. Okay, and there they show in binary classification that unlabeled data doesn't really help. As our first theorem, we show that if you have any bounded loss function, then you have an approximate equivalence in sample complexities between pack and distribution fixed pack. Okay, so knowledge of the marginal, this can only decay your sample complexity by at most a log 1 over delta factor, okay, where delta is your confidence parameter. And so this refutes the power of unlabeled data. And I want to emphasize that's from a worst case perspective. Okay, in certain cases, unlabeled data can help you. But from this worst case pack perspective, you're not gaining a whole lot from knowing unlabeled data. Okay, so in this sense, the landscape of kind of learnability, the landscape of sample complexities really doesn't change. Learning doesn't really get a lot easier at a statistical level. But it turns out it does give you proper learning, and kind of proper learning via SRM. So as our theorem, we show that if x and h are finite, and you have a metric loss function L, then in this distribution fixed model, all classes have optimal randomized proper learners following something called distributional SRM. Okay, so before I tell you what distributional SRM is, let me refresh your memory on classic SRM. So this is the case in which a learner chooses a regularizer psi from your hypothesis class to the real numbers. that you think of as encoding the complexity of hypotheses in H. Okay, an example would be something like L2 regularization. I'm sure you're familiar. And then at test time, your learner emits a function that minimizes empirical risk, I'm denoting L sub s, plus my regularizer psi. So it's kind of, let me balance simplicity of my hypothesis with also empirical performance. And since we're in the realizable case, oftentimes this is the same thing as just minimizing psi, subject to a hard restriction on having zero empirical error. I can oftentimes just normalize psi, and it's just, I restrict to interpolating functions, and I minimize psi. Okay, so this is classic SRM. You might have seen this before. Distributional SRM, actually, before I even show you this, distributional SRM is the exact same thing, but I take the convex hull of my hypothesis class. That's the idea. Okay, so I allow for convex combinations of hypotheses, kind of randomized hypotheses in my class. So formally, my learner picks a distributional regularizer. So this is a map from delta H, so probability distributions on H, to the real numbers. And this is intuitively the complexity of a randomized hypothesis. Then my learner emits kind of the same thing as in classic SRM, the simplest hypothesis that has perfect sample performance. Okay, so just to drive the point home a little bit, it's really the same recipe as classic SRM. I'm just kind of taking the convex hull of my class. Okay, so this is really the natural generalization of SRM to randomized learners. This captures, for instance, Bayesian learners by once I have a prior, taking my regularizer to be KL divergence. It's not too hard to see you get a Bayes update. That's also a key part in the proof, because whenever the adversary picks a prior, your best response is a distributional regularizer. And so I want to be upfront. A big limitation here is that X and H are finite. We suspect this can be generalized to infinite domains X, infinite Y, H. You just kind of need to get the right analytical or topological arguments, we think. But I want to emphasize there's no dependence on the cardinality of X. There's no dependence on the cardinality of H. Really, because if there was, I couldn't have said the word optimal. So to recap, if we're in the distribution fixed model, the learners understand the unlabeled data. Doesn't change sample complexities a whole lot, but we close the proper improper learnability gap. That's really the upshot. We close this gap. So that's kind of one strategy. I strengthen my learner to close this gap. Another strategy is, let's go back to the classic PAC model. We do have a gap in learnability between proper and improper learners. And let's try to understand these additional conditions. Maybe I can, again, get something like a properized DS dimension. I think that would be pretty awesome. So can we design properness dimensions for characterizing proper learnability? We provide some pretty strong evidence that the answer is no. In particular, I'm going to show kind of 3 results that show that proper learnability is a very kind of convoluted and nasty condition. And you can't detect it using a dimension kind of formally a property of finite character. So I'm not going to get too deep into that right now. So the first result is that proper learnability can be undecidable. So there exists a class H such that it's undecidable whether H is properly learnable. Okay, so it can be neither proven nor disproven within kind of the ZFC axioms whether H is properly learnable. The second one is that there exist hypothesis classes on the same input and output space such that their restriction to any finite subdomain is exactly the same, yet one of them is properly learnable and the other one is not. Okay, so proper learnability, it's not a local property. If I'm just looking at behaviors on finite domains, I can't distinguish between one class that's properly learnable and another class that's not properly learnable. And lastly is monotonicity. We show that proper learnability is not preserved by containment in either direction. Okay, so I can have a hypothesis class that is properly learnable. I expand it. It stops being properly learnable. I expand it one more time, and now we're properly learnable again. So there's kind of nothing you can say about inclusion in proper learnability. Okay, in fact, all of these proofs hold even for multi-class classification problems on infinite label sets. I'll try to give you a rough proof idea. I'll just mention that the key ideas here are EMX learning from Ben David et al. 2019, and also the first cancer class from Daniele and Chalev-Schwartz. Those are really the tools that we're using. So let me give you the proof idea. So Ben David et al. Showed that something called EMX learning can be undecidable, can have very nasty properties. EMX learning is phrased in the following way. You have an underlying set X. Your adversary selects some discrete distribution on X. The learner then observes a sample that's drawn from D, and it has to emit a finite set in X with hopefully large D measure. Okay, so it needs to guess the rest of these black points using any arbitrarily large finite set. Okay, that's EMX learning by some kind of seminal work a couple years back. That can be undecidable. I'm going to show that EMX learning is really kind of a multi-class classification problem in disguise. Okay, proper problem in disguise. I do that in the following way. I'm going to have a classification problem where my domain is X, and my label set is the power set of X plus this star label. Then for every subset A of X, I can define a classifier that on inputs that are in A, outputs the label A, otherwise outputs the label star. Okay, and then my hypothesis class is all functions such that A complement is finite. So to give you a little bit of intuition, the key idea is that anytime I see a label that's not star, that's really the signature of the ground truth function, and I'm done learning. Just boom, I'm done. Okay, the second key point is that using hypotheses in my class, I can express the star behavior on any finite subset that I want. Okay, I define my hypothesis class to have these two key properties. Now, the intuition behind learning H is that by the first thing that I said, I can assume that I only see the star label in my train set, because otherwise I'm done. Given that I only saw the star label in my train set, informally, I'm probably only going to see the star label in my test set. Okay, so I really just want to hit the test stars. So my learner's goal is to hit as many of those stars in the test set as it can. Using hypotheses in H, using my properness requirement, I can output star on any finite set that I want. Okay, and that's just exactly EMX learning. Okay, I'll quickly close with some open questions. I mentioned our key limitation before, finite X and H. It'd be nice to generalize this distribution fixed proper learner to more general spaces. It would also be nice to de-randomize it, maybe make it really algorithmic. Right now it's more of a structural statistical result. Again, algorithmic principles for proper learning. And even though we kind of can't get an exact on-the-nose characterization of proper learning, maybe I can get some interesting necessary or sufficient conditions to try to roughly sandwich it as best I can. And that's everything I had. Thank you.
Hey, questions?
So what's a randomized proper learner? It randomly outputs a hypothesis, or it outputs a distribution which at test time you sample from that hypothesis and then output, I guess they're equivalent?
Yeah, I think for the learner that we construct are equivalent. But
okay.
Yeah, so our learner, maybe in general it's not obvious whether you can kind of couple these. But yeah, learner, you can either think of it as it always outputs a total function that is an H, or you can think of it as point-wise, it's kind of always agreeing.
Do you need randomness there? Like, can you have that same theorem with the deterministic proper learner?
Yeah, so that's the first bullet point.
I see. Yeah. Okay.
No, I think that's a very good. I would love to see it de-randomized. Yeah, I would love to see it generalized and de-randomized. I think, yeah, it might just be an artifact of the proof.
Yeah, this was basically my question too. Do you have at least like a bound on the support of the distribution? Like I assume this is coming from some like minimax style thing or something. And often you can sort of bound support on these games. So can you say this is small or?
Yeah, what do you mean by bounding support of the randomized learner?
Yeah, of the output. Like how many pure strategies is here?
How many pure strategies it's using?
You can sometimes bound the support in these theorems.
Yeah, I think we haven't thought about that yet. Yeah, so right now the current proof we have doesn't say too much about how many you're combining. Yeah, I mean, the basic kind of proof idea is that, yeah, you can kind of restrict focus to a game in which, the column player is picking this ground truth over H stars. Yeah. The row player responds with, a distributional regularizer, kind of Bayesian learner. And then you have minimax, and the key idea is you can kind of collapse any mixed strategy to a pure strategy. Yeah, to your question, how many mixed strategies do I need to collapse? Yeah, I'm not sure off the top of my head, but it's a good question.
Okay, let's thank the speaker again for 2 great talks.